In the previous lecture, we considered the problem of cascades of defaults in interbank loans. We discussed how the model of global cascades due to Duncan Watts can be adapted to describe situations where contagion occurs because of counterparty default risk or because of overlapping portfolios. In both models that we considered, stress was propagated from a bank to other banks only after the default of the first bank. So in this lecture, we will discuss instead a model where contagion can occur even before the default of a bank. So a bank can pass shocks to its counterparties before it defaults. The idea here is that if I lend money to someone else, and then this person is in trouble, then the probability that the person will default increases, which makes the contract associated with the loan worth less. Okay, so the idea is that there is the credit quality deterioration causes a devaluation of interbank assets that should be taken into account in order to model the propagation of shocks. So shocks can somehow travel through the system even before an actual default is triggered. So to try and capture this fact, in 2012, Battistone and co-workers introduced this algorithm called debt rank, because it is essentially an algorithm based on centrality like PageRank. So it's an iterative algorithm inspired by Google PageRank, where stress propagates between banks even in absence of defaults. And again, the model is trying to describe the situation of direct relationships between banks, meaning the situation where you have a contract between two parties, so not related to overlapping portfolios, but more to the type of situations we considered in the case of interbank loans. So this is was introduced as a tool to see the buildup of systemic risk before defaults start occurring in the system, and to rank banks in terms of their systemic importance. The idea of that rank is that we start at time equals 0 with a system which is described by a matrix of interbank assets, a vector of external assets, and a vector of liabilities. So for each bank we have its external assets, its liabilities, and then we have a set of counterparties and the corresponding amount of money that was lent out of these counterparties. Then at iteration 1, the system is hit by some shock coming from the outside, so it could be the devaluation of the external assets for some banks, or it could be the default of a bank. And banks that suffer losses induce losses to their creditors. So that rank in particular assumes that losses are propagated linearly from borrowers to lenders. So the interest, as usual, is the one of describing how the initial shock affects the system and under what conditions it can be amplified by the endogenous dynamic of the system. So the specific function to propagate losses that is used in that rank is a linear function. So we can define the relative equity loss for bank I as this quantity hi. Hi of t is the difference between the initial equity of the bank and its equity at time t. So this is an iterative algorithm. So the time is t is the it's a discrete time that represents the iterations of the algorithm. So it's the difference between the initial equity and the equity at time t divided by the initial equity. So it's the relative loss of equity between iteration 0 and iteration t. So this is a positive quantity because the equity, so we are considering losses, so the equity is just decreasing over time. So the propagation of shocks that is considered for the dynamic here is a linear propagation of shocks. It's a strong assumption, but it's the simplest assumption. So it's it's a useful one. So the idea here is that if a borrower suffers a loss of X% in terms of its equity between time 0 and time t, this will translate into a loss of X% for the claims, for the value of interbank claims associated with this bank. Okay, so if Bank J loses 10%, then people who lent money to Bank J, or other banks who lent money to Bank J, will lose 10% of the amount that was lent out. So this is represented by this red response function here in the plot. And this has to be contrasted with the case of the threshold model, which is here denoted by the blue line. The threshold model in the context of interbank contagion is also called the Furfine model. So in the case of the threshold model, there is no loss for the creditor as long as the relative loss for the borrower is smaller than 1, meaning that the loss is smaller than the equity, and therefore no propagation takes place. In this case, we are, in the case of that rank, we are in the opposite limit, where even a very small loss for the borrower translates into a loss for the creditor. So if one starts from the balance sheet identity, now here Wij, by the way, is just the value of the interbank claim. So it's the value of the interbank asset of I that corresponds to the loan from I to J. So the balance sheet identity for bank I reads as in the first equation of this slide. So the equity of bank I at iteration t is just its interbank assets that are assumed to be constant throughout the iterations, minus the liabilities of bank I that again are considered constant, plus the sum over J of the current value of interbank assets. And the current value of interbank assets can be related to the value of to the initial value of interbank assets by the second equation. So Wij at time t is equal to Wij at time 0 times the ratio between the equity at time t minus 1 divided by the equity at time 0. So if at iteration t minus 1 bank J has experienced a certain loss, this will translate into a loss or into a devaluation of the interbank asset Wij at time t. Therefore, one can write an equation for the change, for the relative loss between time t and time t plus 1, which is described by the equation for this quantity delta h I t plus 1. And it's a relatively simple equation in which the loss between time t and time t plus 1 for bank I depend on the losses between time t minus 1 and time t of its counterparties, weighted by this matrix lambda ij, which is called the matrix of interbank leverage, which was introduced in a paper by Derrico and co-workers, which is referenced at the end of this presentation. So the matrix of interbank leverage basically relates the current loss of borrowers to the future loss of lenders. So now we have a very simple equation, which is a linear equation. Delta h at time t is equal to lambda times delta h at time t minus 1, where delta h is a vector. It has a fixed point at delta h equal to 0. And the stability of this fixed point simply depends on the largest eigenvalue of the matrix of interbank leverage. If this largest eigenvalue is larger than 1, then shocks will be amplified. Otherwise, they will not be amplified, but they will eventually, they will be progressively reduced through the iterations. And if the largest eigenvalue of the matrix of interbank leverage is smaller than 1, then one can also compute the fixed point for the quantity h as the inverse of the matrix 1 minus lambda times the initial shock. So as a very simple example, if the system is homogeneous, so all the matrix of interbank leverage is such that every bank has the same interbank leverage, so the sum over J of lambda ij is equal to L for all banks, then the largest eigenvalue of lambda is just the interbank leverage, which is the same for all banks, so shocks will be amplified if this quantity is larger than 1. In the case of heteroshreni networks, we have something similar, but now we have to somehow to take average quantities into account. So we have an heteroshreni network with average degree k and a distribution of weights with a finite second moment. Then in the limit of large networks, the largest eigenvalue can be approximated as the product between the average degree and the average of the entries of the matrix of interbank leverage. Actually, this is the average of the non-zero entries. So it's conditional on a loan existing between I and J. And so the system is unstable if the product between these two quantities is larger than 1. So it is also possible to use results related to the Perron-Frobenius theorem to derive some general results related to the stability of the dead rank dynamic. So in particular, a network is said to be strongly connected if there is a directed path connecting each pair of nodes. And because the matrix lambda has non-negative entries, because lambda ij is the value of the amount of money that I lent to J divided by the initial equity of bank I, so all entries of lambda are non-negative. If the network corresponding to lambda is strongly connected, then its largest eigenvalue is real and positive. That is comes from linear algebra. And from the Perron-Frobenius results, we know that the largest eigenvalue of the matrix is between the minimum over I of the sum over J of lambda ij and the maximum over I of sum over J of lambda ij. So this is in practice never useful, because the minimum is usually smaller than 1 and the maximum is usually larger than 1, so this condition is too loose in order to be used to make practical predictions. However, or practical assessments of the stability of a given network. However, a sufficient condition exists for having a largest eigenvalue of the matrix of interbank leverage, which is larger than 1. And this sufficient condition is that there exists a node I and an integer s, such that the element I of the of lambda to the power s is larger than I. So lambda to the power s element I is related to the sum over all loops. It's essentially the sum over all loops of length s from I to itself, and then for each loop you multiply the elements of lambda ij. For each loop you have a weight that corresponds to the product of the weights of the links associated with the loop. So the intuition here is that if there is a path from a node to itself and the product of the weights along the path is larger than 1, then shocks will be amplified by the loop. However, even if the product of the weights along a single loop is smaller than 1, then the system is not necessarily stable, because in this condition what counts is the sum over all loops of length s. So what might happen is that we have many loops that do not necessarily cause instability by themselves, but because of their combined effect, they actually cause an instability for the system. Diversification also in this case has two effects, because if a bank increases diversification, for instance by adding a link and keeping constant its total interbank assets, so this just means that the bank is lending the same amount but to one to a larger number of counterparties. So this reduces the strength of existing loops because they involving that node, and this can improve stability. On the other hand, by adding a link, what can happen is that we create new loops that combine with those that already existed, although some of them might be weaker, can make the system unstable. So this is a simple example, a toy example, so this is a system where the largest eigenvalue is roughly 1.55 times W, where W is a certain amount of money and is used as a unit of reference here. And now imagine that so here bank 3 is lending an amount 2W to bank 2, and now we imagine that bank 3 decides to lend W to bank 2 and W to bank 4. So what happens here is that the bank 3 is more diversified, and the product of the paths, sorry, the product of the weights along the loop that goes from 2 to 3 and from 3 to 2 has gone down, because before it was W squared, now it is W squared over 2. However, a new loop has emerged between bank 3 and bank 4, and so the combined effect of the presence of these two loops actually leads to, or is related to, the fact that the largest eigenvalue of the matrix of interbank leverage has gone up. So in particular, by tuning W, we can have situations where the network in the left is stable, and the network in the right that has emerged as the result of the attempt of bank 3 to reduce its individual risk is actually more unstable overall. So an experiment that one can make is that of considering a network which is a directed acyclic graph, so for which the largest eigenvalue is 0, so the network is stable, and then start adding random links. Start adding random links, making sure that the leverage, the interbank leverage of each bank remains constant. So each bank is just spreading the same amount of investment across more counterparties whenever a link is added. And so if we do that, we can see that as we increase the density of the network by adding links, although the individual risk of each bank is actually going down, because banks are more diversified and they are lending the same amount in the system, overall the system tends to become more unstable. Here we are plotting the largest eigenvalue of the matrix of interbank leverage versus the density, and okay, the different lines are different realizations of this random process, and we see that of course there is some noise, but overall the tendency is that of going from a system which is stable because the largest eigenvalue of the matrix of interbank leverage is below 1 to a system which is unstable. Of course, adding a link does not necessarily increase the instability of the system. It depends, because as we said, there are two competing effects that are playing at the same time. So depending on the specific link that is added, this might result in increasing or decreasing the stability of the system, but on average the tendency is that the one of going from a stable system when the density is low to an unstable system when the density is large. So here is an example of a process where, or a situation in which the in attempt of banks to reduce their own risk by increasing diversification actually leads to an increase in systemic risk, which is measured by the instability of the metrics associated with the process that describes the propagation of stress into the system. Now, the difference with respect to the models that we have looked at in the previous lectures, where by increasing diversification the behavior was non-monotonic, is in the fact that in those models we had a threshold, and so by increasing diversification at some point we were reaching the point where the initial shock was not propagated anymore because no banks were experiencing losses that were exceeding their threshold. So, however, if, as we do in this case, consider the situation in which losses do propagate even in absence of default, then this non-monotonicity disappears and the system just goes from being stable to being unstable as the density increases. So the diversification grows. So to wrap up this simple analysis of this linear model that rank, the stability of the dynamics depends on the largest eigenvalue of the matrix of interbank leverage. There is also a paper by Marcose et al. That was published in 2012 where they show that something similar happens also for the case of the threshold model that we discussed in the previous lectures. When the eigenvalue of the interbank matrix of interbank leverage is larger than 1, then shocks are amplified by the dynamics, otherwise shocks are progressively reduced throughout the iterations of the dynamic. So I want now to show a case study which is taken by a paper written by Bardoscia et al., which is referenced at the end of this presentation. So the case study is about an application of this debt rank to the study of European banks, where we consider 183 European banks that were publicly traded between 2008 and 2014, and there's information on the total interbank assets, liabilities, and Tier 1 capital for these banks. So Tier 1 capital is a proxy for the equity. So in this data there is no information about who the counterparties of each individual bank are. There is only information about how much each bank is lending to other banks and borrowing from other banks, but no higher resolution. So there are methods that can be used to reconstruct a plausible structure of the network of interbank lending, which is compatible with the constraints imposed by the data on the aggregate interbank lending and borrowing for each bank. So this model is known as the fitness model. So the idea is that we can define two quantities for each bank, AI and LI, where AI is just the share of interbank assets that belong to bank I, so it's the total interbank assets of bank I divided by the total interbank assets in the system, and the same for liabilities. LI is the total interbank liabilities of bank I divided by the total interbank liabilities in the system. And we can construct an ensemble of networks by assuming that the probability that I lends to J is given by the formula here at the bottom. The idea of this formula is that if I is a large lender and B is a large borrower, then the probability that I lends to J is higher with respect to the case when, for instance, I is a small lender and L is a small borrower. So the idea is that AI and LI are kind of fitnesses for bank I, and then an adjacency matrix can be written just by drawing random numbers and compare them with these probabilities. Once an adjacency matrix has been obtained, one can use the RAS algorithm to populate the entries of these the non-zero entries of these adjacency metrics. So it's basically a way to assign weights to the non-zero entries of these adjacency metrics in such a manner that all of the constraints provided by the total amount of interbank lending and borrowing of each bank, which are known, are satisfied. So then we can perform a sort of stress testing exercise on this ensemble of reconstructed networks. So here is one example, and in particular here we are taking the network for different years between 2008 and 2013, and then measuring the response of the system to a certain exogenous shock. The exogenous shock is basically the devaluation of 5% of assets for all banks. This devaluation is not small because banks tend to have a high leverage, so a devaluation of 5% might translate into a significant devaluation at the level of the equity. And indeed, you see here that the shock is roughly affecting 20% of the equity of each bank, the exogenous shock. This is the line at the bottom. And okay, then if one runs the algorithm, it is possible to see that this contribution of the network to the final losses is actually significant. If one were to run a stress testing exercise without taking into account network effects, then it would greatly underestimate the result. Then the result would greatly underestimate the possible losses that can be observed in the system. So it is also possible to rank banks through that rank. And the idea here is that one can perform several stress testing exercises by every time assuming that a different bank defaults and then measuring the impact that that default would have for the system. And on the other hand, measuring the average impact experienced by a bank when another bank is selected as trigger for the exogenous shock. So basically, we can rank banks in terms of their systemic importance, their impact on the system, that's the losses they would cause if they were to default, and in terms of their vulnerability, that would be the losses that they would experience if one other bank were to default. And basically, what we see is that if we so in this plot there is a scatter plot of the ranking in terms of vulnerability and in terms of impact, and in the top right corner we have banks that are highly vulnerable and highly impactful. So of course these banks are kind of the worst possible banks from a systemic point of view, because they are the most vulnerable in the system and at the same time the most impactful. So they can easily be affected by shocks that start somewhere else in the network, and they will affect other banks significantly after they have been affected. And the point here to notice is the fact that the size of the circles is related to the size of the bank in terms of total assets. So, of course, there are some big banks that are among the mostly systemically important. So there are some big banks that appear in the upper right part of this plot, but we can also see that there are some very small circles in the upper right part of this quarter of this plot. So we see that small banks can or relatively small banks, of course, these are all large banks, but say relatively small banks can also be systemically important. So there is more to systemic risk than just the size of a bank. And that rank, so we discussed in the last lecture this idea of too interconnected to fail. That rank somehow takes it even further, because it's not just interconnection that matters, but it's centrality. That rank is essentially a measure of centrality. So the idea here is that there are banks that maybe are not very big, but they are very systemically important because they are central in the network. So they are kind of too central to fail. So here there are some references related to that rank and the results that we have discussed in this last lecture.